In Lesson 99, we'll talk about blackbody radiation and the photoelectric effect. Now, we've talked about ideal gases, we've talked about ideal fluids when we were studying Bernoulli's equation, and there's some certain assumptions that we make about those fluids. They may not be the most realistic assumptions, but they're close enough to allow us to develop formulas that we can use as our foundational formulas in the study of that particular topic. Basically, a black body is an ideal body that absorbs all visible forms of electromagnetic radiation. Maybe you haven't really thought about this before, but that's what makes something that you look at black. It's black because all of the light coming in and hitting it is absorbed. Nothing gets reflected to your eye. That's why you see black. So this ideal black body absorbs all visible electromagnetic radiation. Now that's easy enough to understand why it would be called a black body, but we can also make an assumption that it absorbs all EMR, not just visible EMR, but all EMR, all the gamma rays, all the radio waves, all the microwaves. Every EMR gets absorbed by it. That would be an ideal black body. Now an ideal black body also releases some EMR back. We say that the EMR released is proportional to the temperature of the black body. That's not an alpha symbol there. That means proportional to in this case. The EMR released by a black body is proportional to the temperature of the black body. Max Planck used an ideal black body to come up with his formula E equals H times F. And it also helped him come up with the idea of a photon of light, basically, or a photon of EMR. Albert Einstein used Planck's studies on blackbody radiation to help him come up with the photoelectric effect. And basically, what that is for a metal, metals are good conductors. That means the electrons can move freely through the substance. Insulators, the electrons are bound tightly. They can't just move freely. Now, an electron in a metal, it won't just jump off randomly, unless, of course, it had enough kinetic energy to do so. And one way that it can gain enough kinetic energy is for a photon of light to come in and hit that electron and give it enough kinetic energy to leave. The amount of energy required to free an electron from a metal, that's called the work function. And for one metal in particular, tungsten, we know that it has a work function equal to 4.5 electron volts. If we set that equal to Planck's constant, or Planck's formula E equals HF, we can figure out the frequency that a photon of light would need to have in order to free an electron from tungsten metal. And so that frequency would be about 1.09 times 10 to the 15 hertz. If you go back to our table on page 732, you'd see that that frequency is pretty much out of the visible light range. It'd be like an ultraviolet form of light. So that could be provided by the sun. There could be ultraviolet light coming in, freeing an electron from a metal. That's basically one of the reasons metals shine, is because a photon hits them and it releases an electron. That electron is free and it will lose some of its energy. It will release that as a photon, and we see that shining of the metal. Now, photons hitting tungsten, let's just pretend like we had some tungsten right here, and there were photons coming in. Remember, we think of those as just like a little packet of frequencies. Photons come in and hit, and an electron is released. So we'll put a little minus sign there in a circle, showing that electron being released. If those photons are coming in at a frequency below 1.09 times 10 to the 15 hertz, it doesn't matter how many come in, an electron won't be released. Think of it kind of like shaking. It's going to be like a natural frequency or something for that particular metal. It'll shake it at just that right amount so that it can, at one time in its amplitude, it'll pull free and be free of that metal. Now, of course, you could have photons coming in higher than a frequency of 1.09 times 10 to the 15 hertz for tungsten. That would release that photon or that electron as well. So this right here, this 1.09 times 10 to the 15 hertz, that could be thought of maybe as the critical frequency. That's just the frequency needed to release an electron from tungsten. A better formula for any frequency would be HF, Planck's constant basically, or Planck's formula, is equal to this work function value for a particular metal plus the kinetic energy of that electron. This was Einstein's conclusion, and this is known as his photoelectric equation. Let's understand this photoelectric equation a little bit more. We could figure out that kinetic energy of an electron, 1/2 mv squared, using a circuit like this. And we have a voltage source here, V0, and basically this side is the positive, that side's the negative. What I'm doing is drawing the diagram on page 741, and I think actually on page 741 they drew that voltage source backwards. You'll see why in a minute. Up at the top we have two metal plates, those vertical plates. Those are metal. One's a cathode, one's an anode. A cathode gives up electrons more easily than an anode would. So these are probably going to be two different metals. One that gives up electrons, one that will accept those electrons that have been given up. So let's shine a photon onto the cathode. Think about what would happen. That photon hits, and let's say it has more than enough frequency to release an electron. So an electron will travel towards that anode. Now let's just think about this when the voltage is 0. When the voltage is 0, that'll work. There's plenty of kinetic energy there. We said the frequency was higher than it needed to be to allow for some kinetic energy, so it's going to move towards the anode. But then think about what would happen if we started increasing the voltage. If we do that, we'll have basically a negative potential there and positive there. It's going to have to start fighting against an electric field. Think about if that was a closed circuit, and think about electrons flowing. Normally we talk about a circuit, we think of protons flowing out of the positive side. But in reality there's electrons flowing in that direction there. Now there will be a voltage. If we can just continue to increase that voltage, we can just keep going up, 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 up until the current in this circuit equals 0. There's no current at all. So we stick an ammeter in somewhere. Let's just put one right here. And we measure the current. So probably what's going to happen is we'll have a negative current being measured as those photons hit and release electrons up to the point when V0 provides enough energy to make the current equal to 0. If we keep increasing V0, we'll get a positive current. This type of circuit can be used to figure out what 1/2 mV max squared is equal to. When the current is 0, then we set that equal to the charge times voltage, electron volts, E times V0. That changes our photoelectric equation to H times frequency is equal to the work function plus E V0. We can rearrange this and solve for that voltage, and that's equal to H over E times the frequency of that particular EMR photon minus the work function over the charge. Now that's a linear equation there. Y equals mx plus b. V0 equals H over E, which is a constant, times the frequency, which is variable, minus the work function over E. So as the frequency increases, basically, the voltage required to stop the flow of electrons, stop the kinetic energy of the resultant electrons, that changes as well. One thing that we can see here is a total deductive process, and inductive as well, by scientists. Max Planck came up with that H times F relationship. That equals the energy of a photon. Einstein came up with this photoelectric equation. He published that in a journal in 1905 at the same time that he published his special theory of relativity. In 1913 and 1914, an American physicist, Robert Millikan, he basically developed this equation. He used that voltage relationship to confirm Einstein's photoelectric equation. So these scientists built on what they had learned from other scientists. That's what deductive reasoning is. And they also used inductive reasoning. They created new rules, basically. That's what inductive reasoning is about, the process of finding a rule. They based that on observation as well as just deductive reasoning. Basically, they used deductive reasoning to come up with their hypotheses, and then they did their experiments, made their observations. A hypothesis, if you recall, that's an educated guess. So in the scientific method, that's where you use deductive reasoning. That's where these scientists use deductive reasoning. They did their experiments. That was the inductive part, and they came up with new rules. There's still lots of new rules to discover using this inductive-deductive process. That V0 value can be considered the cutoff voltage. That's the voltage that needs to be applied for a particular frequency of these incoming photons to stop the flow of electrons off of a cathode. This formula basically led many people to accept the photon theory for light. Classical wave theory, like Maxwell had helped develop, that implies that the waves of any frequency would provide the energy to knock an electron off, provided that frequency was intense enough. In other words, its amplitude was great enough. These experiments basically showed that that was not the case. And this led many scientists to confirm that the quantum theory of physics was the appropriate one. We still think of light as having a dual nature. It has photons, and also we think of the electromagnetic wavelengths too, the electric field wavelength and the magnetic field wavelength perpendicular to that. Let's go ahead and do a practice problem here. If we had a photon of electromagnetic radiation coming in at a particular frequency, we didn't know that frequency, but we knew the kinetic energy of the electron as it left. We knew what the work function for that particular metal was. What would the frequency be of that particular photon? Well, let's just think about our photoelectric equation. HF is equal to the work function plus the kinetic energy of that particular photon or the electron as it leaves. So we could just say that HF is equal to 4.2 plus 1.9. The work function, remember, that's the energy required to remove the electron. We can assume that energy is conserved here. There's no heat loss or anything like that. So all of the energy put in by that photon, some of it goes into releasing the electron. What's left over goes into accelerating that photon to its kinetic energy of 1.9 electron volts. So we want to solve for frequency here, and that means we'll have Planck's constant. Well, let's just say F is going to be equal to 6.1 over H, and we'll have to have Planck's constant that deals with electron volt seconds, 4.136 times 10 to the minus 15 eV times seconds. our numerator is in electron volts, so the electron volts are going to cancel. We end up with 1.47, or about 1.5 times 10 to the 15 hertz. That's the frequency of this electromagnetic radiation. So that would basically be an ultraviolet form of EMR, it'd be ultraviolet frequencies outside the visible spectrum. Remember, we said that's what makes metals shiny. If you've ever noticed, metals are usually shinier outside in sunlight than they are inside the house. That's because there's more of these high energy wavelengths outside from the sun. Those hit the metals, release electrons. Those electrons can lose some of their kinetic energy, which is released as light, and that's the shine that you see. Okay, well that's all for lesson 99.